An open parachute, the reflective surface of a flashlight, the arc of a basketball shot are all examples of real-world situations that require a quadratic function to model their behavior. Hi, my name is Tom Atwater, and today we are going to be investigating functions and modeling, and in particular linear and quadratic functions. Let's start off with a definition of a polynomial. Let n be a non-negative integer, and let a sub 0, a sub 1, a sub 2, all the way through a sub n minus 1 and a sub n be real numbers where a sub n is not equal to 0. Then the function given by f of x is equal to a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, all the way through a sub 2 times x squared plus a sub 1 times x plus a sub 0 is a polynomial function of degree n. The leading coefficient is a sub n. All right, now, the 0 function, f of x is equal to 0, is considered a polynomial function, but it has no degree and no leading coefficient. Let's try out the idea of figuring out if something is a function or not. Which of the following are polynomial functions? For those that are polynomial functions, state the degree and the leading coefficient, and for those that are not, explain why they're not. All right, part A, f of x equals 4x cubed minus 5x minus 1/2. That is a polynomial function. It has degree 3, and it has a leading coefficient of 4. Now, g of x equals 6x to the negative 4 plus 7. It's a function, but it's not a polynomial function because of the negative exponent. Part C, that is also a function, but it's not a polynomial function because the square root of the 9x to the 4th plus 16x squared, the problem is it's not going to give us integer coefficients. And so that is not a polynomial function. And part D, the k of x equals 15x minus 2x to the 4th, certainly is a polynomial coefficient. The degree is 4, and the leading coefficient is negative 2. All right, here are a few familiar polynomials functions whose study we will take up in this section. Starting off with the 0 function, we've already talked about f of x equaling 0, and that's undefined. That is, the degree of it is undefined. Whereas the constant function, f of x is equal to a, and in this case, a cannot equal 0, that has a degree of 0. So there's a difference here. The constant has a degree 0. The 0 function, f of x equals 0, is undefined. Let's take a look at linear. A linear function, f of x equals a times x plus b, where a doesn't equal 0, that has a degree of 1. Quadratic function, f of x equals ax squared plus bx plus c, where again a does not equal 0, that has a degree of 2. Now let's revisit and take a closer look at the properties of linear functions. A linear function is a polynomial function of degree 1, and so it has the form f of x is equal to a times x plus b, where a and b are constants and a does not equal 0. If we use m for the leading coefficient instead of a, and if we let y equal f of x, then this equation becomes the more familiar slope-intercept form of the line y equals mx plus b. Let's do an example of this where we find a linear function of f such that f of negative 5 is equal to negative 1 and f of 2 is equal to 4. In this particular case, what we want to do is find the slope, and the slope is equal to the change in the y values, or in other words, in this case, the change in the f of x values. So we have f of x values of negative 1 and 4. So I will take 4 minus a negative 1. And then the x values are going to be 2 minus -5. So on the top, we have 4 minus a -1. The two negatives become positive. 4 plus 1 is 5. And then on the bottom, we have 2 minus a -5. Again, double negatives positive. 2 plus 5 is 7. So the slope of this particular line is 5/7. And our equation would become f of x is equal to 5/7 x plus b, which is our y-intercept. But we can figure that out because all we need to do is take one of these 2 points, plug it in for x and f of x. So let's just take the first one. F of x is -1. That's 5/7 times x. And in this case, x is -5 plus b. So when we multiply the -5 times the 5, we'll get -25/7 right here. So I have -1 equals -25/7 plus b. So I have to add 25/7 to both sides, and that's going to give me, when I bring the 25/7 over here, I change the -1 into -7/7. So it's -7 plus 25, which is 18/7, is equal to b. Let me just get rid of a little bit of that. There. Okay, so I'm going to now write my particular function, f of x, and it's going to be, let me get rid of all of this and rewrite it. It's going to be equal to f of x equals 5/7 x plus 18/7. And that's my formula for it. Now, we know that it's right, but if we wanted to check to make sure, we could take our other point, which is the point x equaling 2 and f of x equaling 4, and I could plug those in. In other words, does 4 equal the 5/7 times 2, that's my x value, plus 18/7? Well, of course, right here, 5 times 2 is 10. We have 10/7 plus 18/7. 10 plus 18 gives me 28/7. And in fact, it checks because 28/7 is equal to +4. So 4 equals 4. All right, so that's an example of finding a linear function given 2 particular points that are part of that function. Now, let's take a look back at rate of change, but using the function notation. So we have average rate of change. The average rate of change of a function y equals f of x between x equals a and x equals b, where a does not equal b, is given by f of b minus f of a over b minus a. Let's relate this to linear functions. Constant rate of change. A function defined on real numbers is a linear function if and only if it has a constant non-zero average rate of change between any 2 points on its graph. The rate of change of a linear function is represented by m in the formula f of x is equal to mx plus b. The initial value of f is f of 0, which is represented by b, which is the y-intercept. All right, here's a summary of what we've been looking at so far. Characterization of the nature of a linear function. If we look at it from the point of view of just saying it verbally, it's a polynomial of degree 1. What if we look at it from the point of view of algebraically speaking? In that case, the characterization is f of x is equal to mx plus b, where m does not equal 0. How about graphically? If we look at it from the point of view graphically, then we say that it's a slant line, right? Slant line with a slope of m and a y-intercept of b. And finally, what if we look at it analytically? In that case, it's a function with a constant non-zero rate of change, which we would call m. F is increasing if m is positive, and it's decreasing if m is negative. The initial value of the function is still f of 0, but in this case, it's equal to b, which is, of course, the y-intercept. Well, now it's time to revisit linear regression. And we're going to look at the properties of the correlation coefficient r in a linear regression. We have that r has to be between -1 and 1 inclusive. When r is positive, there is a positive linear correlation. When r is negative, there's a negative linear correlation. When the absolute value of r is approximately 1 or it's close to 1, then we say that there's a strong linear correlation. And when the absolute value of r is close to 0 or near 0, then it is a weak or maybe even no linear correlation at all. Well, it's great to say all of that, but what would that look like in terms of a graph? Here, we'll take a look. In this example, on the far left, we have a strong positive linear correlation because, as you can see, the pattern of the scatter plot appears to look like the line that I've just drawn in red. And it's very close to that line, so we're looking at a fairly strong positive linear correlation. In the next one, although they seem to appear to all go in a direction of this oval, if I draw a line, you'll see that some of the points are close to it, but other points, like these, are further away. And in this case, we're saying, okay, there seems to be a positive linear correlation, but it's kind of weak. Now let's take a look at little or no correlation. You can see that what happens is all of the dots are scattered, and we can't really draw a nice oval. In fact, it's approaching a circular shape where we can't draw a conclusion other than there does not appear to be any correlation. Well, what about the negative correlations? Let's look at two graphs that go through what that would be like. So what we have is a strong negative linear correlation with this one right here. You can see that if I draw a line, the points are very close to it. And it's negative because the slope is negative. Over here, if I try to draw a line and splitting the difference, you can see that there are many points which are not close to the line. So although there appears to be a negative correlation, it also appears to be that it's not very strong. That is, it's weak. Well, now let's look at the procedure for doing a regression analysis. And the procedure is this. You take your graphing calculator, you enter the data into the lists, L1 and L2, and then you plot the data on a scatter plot. Then, using the calculator, step 2 is you find the regression model that fits the problem situation. Then, after you find that, you enter that model into the equation editor, using the Y key, because then you superimpose the graph of the regression model onto the scatter plot. And that way you can actually see the graph itself as it relates to the data. And then step 4 is you use the regression model to make predictions of that's called for in the problem. That is, you answer the question that they've asked you for. So let's try out this procedure on a specific example. Use the data in table 2.2 on the following slide to write a linear model for demand in boxes sold per week as a function of the price per box, which is in dollars. In particular, describe the strength and direction of the linear correlation. Then use the model to predict weekly cereal sales if the price is dropped to $2 per box or it's raised to $4 per box. So let's take a look at this table and just get a sense of what's going on. We have the price per box over here on the left-hand side, and we see that a price of $2.40 yields 38,320 boxes. And just pick another one. As the price goes up to $3, you can see that the number of boxes sold has dropped off. Well, we enter these into our lists, L1 and L2, and then we do a scatter plot. And that would look like this right here. We run the regression analysis, and in this particular case, let me write out what I got for the regression analysis. It was y equals negative 15,359, approximately. I've rounded that off. X, then plus 73,000, and I'm going to run out of room over there, about 622. And so that's why you see that the window that I've selected is running from 10,000 to 40,000 because I needed to make sure that I could include this entire graph. So now what I can notice is that I can use this model to figure out the $2 and the $4 per cost, how many boxes of cereal will get sold. But we could use the graphing calculator to help us do that. So let's take a look. In this case, I want to know when x is equal to 2. So I use the trace function, and you'll see that the result it gives me is that they're going to sell 42,000, almost 905 boxes, and that's rounded off. Okay, that's what happens if they decrease the price to $2. What happens if they increase it to $4? I didn't actually do the graph out for you, but I did the graph, and if at $4, the number of boxes that they sold drops to 12,190. That's right, it drops off. So what we're seeing here is that there is a negative correlation, and it's strong. So the price of the cereal greatly affects the number of boxes that would get sold. Let's turn our attention now to quadratic functions. Quadratic functions now have a polynomial of degree 2, and the graph of f of x equals x squared is a parabola. And we've seen this a number of times. In fact, the graph of every quadratic function is a transformation of that basic graph f of x equals x squared, yielding a parabola that either opens upward or downward. Now, the standard quadratic form for a parabola for a function of degree 2, f of x is equal to ax squared plus bx plus c, where if a is positive, it opens upward, and if a is negative, it opens downward. The axis of symmetry is x equals negative b over 2a. And there's another form that we're familiar with called the vertex form of a quadratic function. And in this case, any quadratic function, f of x is equal to ax squared plus bx plus c, where a, of course, doesn't equal 0, can be rewritten in the form of the vertex form called f of x equals a times x minus h, quantity squared, plus k. And in this case, the graph of f is a parabola. The vertex is h comma k. The axis of symmetry is x equals h, where h is equal to negative b divided by 2a. And k, which is the y value, is equal to c minus a times h squared. If a is positive, then the parabola opens upward, and if a is negative, then it opens downward. Let's work an example of where we can apply the vertex formula to the parabola. So we have the following example. Find the vertex and axis of the graph of the function, and then rewrite it in vertex form. The function we have is f of x is equal to negative 3x squared plus 6x minus 5. So let's pick out our a value. Our a value is negative 3. Our b is positive 6, and our c is negative 5. I have more room on this screen, so now we can go to work. The first thing we can find is h. And remember, h is equal to negative b over 2a. So that would be negative b is negative 6, 2 times a, which is negative 3. So that's going to equal then negative 6 over negative 6, which turns out to equal positive 1. So that's our h value. Now, to find k, we substitute in f of h, which in this case is f of 1. And we plug that right into our function. And our function is negative 3 times x squared, so 1 squared, plus 6 times 1 minus 5. So what we have then is 1 squared is 1, that's negative 3. Negative 3 plus 6 is positive 3, minus the 5 gives me negative 2 for the k value. All right, so now the axis of symmetry we said was x equaling 1. And we can write our vertex form, which is f of x is equal to a, which is negative 3, times x minus h, x minus 1, quantity squared, plus our k, plus negative 2, because our k we've calculated to be negative 2. So here's the quadratic function in vertex form. All righty, let's summarize what we've just talked about with respect to quadratic functions. If we take the verbal point of view, the verbal point of view is that it's a polynomial of degree 2. What about the algebraic point of view? We characterized it two ways. We said that f of x was equal to a x to the power 2 plus b times x plus c, or we said the vertex form was f of x is equal to a times parentheses x minus h squared plus k, and in both cases, a cannot equal 0. Well, what about looking at it from the graphical point of view? In that case, we have a parabola with a vertex of hk. We have the axis of symmetry is x equals h. It opens upward if a is positive, downward if a is negative, and the initial value is the y-intercept, which is, of course, f of 0, and that actually ends up equaling c. The x-intercepts you can calculate using the quadratic formula, negative b plus or minus the square root of b squared minus 4ac over 2a. Now, of course, if it factored, you could do it that way as well. Well, you know what? It's time for you to try a problem. What I would like you to do is to find the vertex and axis of the graph of the function and then rewrite it in vertex form. The function is f of x is equal to 3x squared plus 5x minus 4. Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. All right, let's find out how you did on this particular problem. Let me go to this screen where I have more room. Of course, you know that a is equal to 3, b is equal to positive 5, and c is equal to negative 4. So the first thing that I'm going to calculate is my h value. And my h value is equal to negative b over 2 times a. So 2 times 3. That gives me an h value of negative 5/6. Now what I want to do is calculate h. And h is equal to k. We're going to calculate k. And k is equal to f of h. So that's going to be equal to substituting negative 5/6 wherever we see x. So this would be 3 times negative 5/6 squared. Then plus 5 times negative 5 6 minus 4. Let's simplify that a little bit. It would be equal to, well, negative 5 6 quantity squared. First of all, is positive. The top is 25, the bottom is 36. But then we have to multiply the top 25 by 3, so it's 75 over 6. The second term, 5 times negative 5 6, negative 25. I'm sorry, that was a 36. I don't know if I said it, but 75 over 36. This one is negative 25 over 6. And then we have the minus 4 at the end. Common denominator. We have to put these all over the same denominator in order to then be able to add them together. And actually, in this case, if we just stick with the common denominator of 36, we would have 75 minus, in this case, we have to multiply by 6 over 6, so minus 150, then minus, and again, multiply here, let's do 6 over 6, so we get minus 24. I'm sorry, I have to multiply by 36, don't I? So 36 and 36, so I end up with 144, and all of that is over 36. So I then do that, the numerator, I add and subtract all of that together, and when I reduce it down, I'm going to get that it's negative 73 all over 12. That's my k value. All right, so now I have h and k. I know that a is 3, so I can write my parabola in vertex form. So let me get rid of all of this so that I have space. And what I have then is f of x is equal to 3 times x minus negative 5 6 quantity squared, and the negative 5 6, of course, is the h that we calculated, minus 73 over 12. And that was the k that we calculated. So that's the vertex form of the quadratic function f of x equals 3x squared plus 5x minus 4. If that's the answer you got, great job. All right, in today's lesson, we explored polynomial functions, and in particular, linear and quadratic functions. And for the quadratic function, we looked at the vertex form and standard form, and we revisited linear regression with respect to linear functions. All right, be sure to work the exercise that your teacher assigns, and we'll see you next time.